This video is about a project I've been working on for the last couple of weeks. And it's a sequel to a video I made last year about, this was a breadboard prototype of an OctaFuzz, where the octave was controlled by a Digipot using an Arduino. So what a Digipot is and how it all works I'll explain in a minute, but I've decided to separate this project into two things. And the first one is an OctaFuzz, which is built in this enclosure right here, this fake wooden enclosure. And it has a TRS jack built in, so you can hook up an expression pedal to control the amount of octave going to the fuzz. And the other thing is that I wanted to make a digitally controlled expression pedal using a Digipot. Well, a Digipot is a digitally controlled potentiometer, and an expression pedal is no more than just a potentiometer, but then you control it with your foot. And a Digipot is a completely independent circuit, so it's like a relay. You can switch other things with it because it's completely independent. So it's a digitally controlled analog circuit, and it's divided into 256 steps. And this Digipot has a resistance of 10 kilo ohms, and that's the same as most expression pedals. The other thing is, this thing you might have seen before in another video of mine. I've programmed something for the Arduino that's inside here. So it's basically a foot controller for the Boss RC3 Loopstation. Well, I decided I wanted to combine those two things. So the Digipot as an expression output and the Boss foot controller. And yeah, it's all combined in this thing right now. So it basically is a controller with 4 foot switches, like you can see, 4 LEDs as well. MIDI input and a MIDI output jack. And as well there's an expression input jack over here. There's a double relay output jack where you can, so you can switch the loop station with it. But you can also do things like tap tempo for a delay, for instance, or you can switch channels for an amplifier. That's also possible with this thing. And the third jack that's on top of this thing is the Digipot output, and that's what this video for today is about. And I will show you how this all works with the OctaFuzz that I mentioned before, with the expression input jack for the amount of octave that you hear. And this thing is a little two-step expression pedal, as you might say. It's a little passive circuit, quite easy to make, and I've also made a video about it. So there are 4 expression modes in this project. The first one is where the expression input is the same as the expression output. So I'll demonstrate this with the OctaFuzz. So the expression is now completely down, and you can hear there's almost no octave present. And when you turn it up, all the octave is there. And you can set things in between. And as you can see, the LED on here also changes when the knob is turned, or the expression pedal. So it's completely on when it's on the toe down position, and it's off when it's on the heel down position. So that's the first mode. It's not quite that interesting yet, but the other modes are a little more exciting, because we're going to start off with the rising sawtooth wave, and it sounds like this. So it slowly goes from 0% to 100%, as you might say. And the incoming expression controls the rate of this LFO. So when it's really slow, it's about 4 seconds. And when it's completely up, it goes really fast. Now the sawtooth wave also has a reverse mode. When you press and hold this button and press that button again, it becomes a falling sawtooth wave. So yeah, that's the reverse mode. There's also the triangular wave shape that also has a cycle duty of about 4 seconds. And it goes up in the same rate as well. And the fourth mode is square wave. So it alters between 0 and 100%. Now this thing also reacts to MIDI tempo. So as you can see, the LEDs blink on the incoming MIDI tempo. On every beat they blink. In mode 1 it's completely independent from MIDI tempo. So you can still turn the knob or put your expression pedal down or up, and it's completely independent from that. But modes 2, 3 and 4 are synced to the MIDI beat. So now the cycle is about 4 beats, but you can also divide it when you press it again. So now it's a cycle of 2 beats. You can divide it again. So now it's a cycle of 1 beat. And when you press it again, it goes back to the 4 beat cycle. It's also available on the other wave shapes. So this is the triangular wave shape. Now it's divided into 2 beats. And now into 1 beat. And back to 4 beats. And when MIDI tempo is present, the reverse wave shape are all available on all the wave shapes. So press the first foot switch, press this one again. So now it starts off on every count on 100%, and on the off beat it's 0%. Same as with the triangular wave shape. following sawtooth wave shape. So yeah, those are the modes on MIDI tempo. And the cool thing is that everything that this thing receives also goes to the output jack of the MIDI. So it's like MIDI through. Everything it receives it also transmits. So let me explain to you how this code actually works. This is the Arduino code that I've written. First of all, you gotta include the SPI and the MIDI libraries, because SPI is the language that the Digipot uses, and MIDI is where it responds to. Yeah, MIDI, incoming MIDI data, of course. So now there are some commands that it reacts to, and some variables and booleans that are used later on. The buttons, so it's not button 1 to 4, but call it button 0 to 3, as well as the LEDs. So on the top left it's button 0 and LED 0. And on the bottom right it's button 3 and LED 3. So in the setup you have to define that it works on a baud rate of 31,250. And this is the baud rate where MIDI works on. And you have to start the SPI. And you have to define what the pins actually do. I've used the internal pull-up resistor of the button pins. And in the loop you will see that it always reads out the button pins as well as the incoming expression, which is connected to analog pin number 5. First of all, you can see what the buttons actually do. When the first button is pressed, it goes into to static mode, which is wave shape 0. And you can also use button 0 as the reverse button when you press other buttons as well. So this code actually makes sure that when you press the button without any other buttons, it goes back to 0. Otherwise you can reverse the wave shape. Yeah, buttons 1, 2 and 3 are almost the same. It selects the wave shape, and you can also reverse the button when you press that one in combination with button number 0. So this is what happens when it does receive MIDI data. So it reads what's incoming on the MIDI input jack. When it's a MIDI clock signal, first of all the sync program is activated, and it updates the clock milliseconds. When there's no MIDI clock present for half a second, it switches back to the mode where the incoming expression data is transformed to the rate of the wave shapes. When sync is activated, let me scroll down through the program. Basically what it does is counts the amount of MIDI clock signals, and there are 24 signals in one beat. And it resets after 4 beats, so that's 96 MIDI clock counts. And other than that, it makes sure that the LEDs blink on count 1, 2, 3 and 4. Let me demonstrate that with starting the MIDI clock here. It's on 90 BPM. And you can see that it blinks on every count. And other than that, when the MIDI start or stop message is received, the counter goes to 95, which means that after the first MIDI clock message is received, it goes back straight to 0, because everything equal or above 96 goes straight back to 0. So it resets immediately after it receives the MIDI start or stop message. So when a wave shape is set to 0, so static mode, it does nothing with the incoming MIDI data. So the incoming expression pedal input is also set to the output. So nothing happens here. So when I go to wave shape number 1, there are 3 different sub-modes, as you can say. are cycle divisions, which means 1, it means that it's a whole note or 4 beats. On 2, it means that it's half a note or 2 beats. And 4 means 1 beat, so it's actually a quarter note. So those are the cycle divisions that are present. Now I've used the basic formula. All that it changes when the different cycle divisions are active is a factor, and it counts the beat. So when I scroll down to the actual formula over here, it subtracts the amount of beat from the counter, and the counter is the amount of MIDI clock that's incoming. So it subtracts the beat from that, and the result of that it's multiplied by the factor. That makes it cycle nicely from 0 to 255 on every cycle. So now that's on the whole note. You can press it again, so it goes to half a note or 2 beats, and press it again for a quarter note. Now the same thing for the other wave shape. So wave shape number 2, that's a triangular wave shape, and it's still on the cycle division of 4. So it's a quarter note cycle division, and this also cycles back to a whole note, and when you press it again on half a note. So it's the same thing, 3 different cycle divisions, and basically the formula is the same. There's also the same factor, only doubled. Now there's also the introduction of the Boolean rise and fall, or the rise is true and the rise equals false. So now it cycles between a rising wave shape and a falling wave shape, and the formula is actually the same. So it counts the amount of MIDI clock signals, subtracts the beats from it, and the result of that it multiplies by the factor. So it cycles nicely between 0 to 255 and slowly back to 0 again. So that's when it rises, and when it falls, 255 is then subtracted by the counter, then the beat, and multiplies by the factor. When the reverse wave shape is active, it's completely the opposite. So it starts off on 255, cycles back to 0 and back to 255 again. Now wave shape 3 is the square wave. Uses the same principle, but there's no actual formula that calculates the amount of Digipot and LED transmission. But this one cycles between 0 and 255, so fully on. And what it only does is it counts the amounts of beats. And when the cycle division is 1, or there's a cycle of a whole note, 4 beats, everything below count number 47, it goes to 0, and everything above it goes to 255, or between 0 and 100%. And for the other cycle divisions as well. So this is the code that tells it what happens when it doesn't receive any MIDI data for a half a second. So that's 500 milliseconds. It goes back to the mode where the incoming expression pedal is converted to the rate of the wave shape. So let me show you. I'll stop the MIDI clock over here, and you can see after half a second it goes back to the other mode. There we go. And now you can set the rate again with the incoming expression pedal. Now when there is no MIDI tempo received, or MIDI clock messages received, when the wave shape is 0, so that's the static mode, incoming expression data is output straight to the expression output jack. On wave shape number 1, which is the sawtooth wave, so it rises in a certain factor set by the incoming expression pedal, and it updates the Digipot and the LEDs every 10 milliseconds. Same goes for wave shape number 2 and number 3, which are the triangular and the square wave. They work in the same manner as the first wave shape. So the incoming expression data is setting the rate of the wave shapes. Now you've seen it on every program. There's this thing called digital pot write that starts this little program over here, which writes data to the Digipot. in numbers between 0 and 255. So that's basically the code, how this little thing works and how it receives MIDI data and sends it back to the Digipot. I will upload this code to GitHub if you are interested in making your own pedal. And if you have any questions, you know where you can leave them. There's a comment section for that. So I'll hope I can answer your questions accordingly.